This is the FRR Workshop. I'm Donald Sharp. I'm one of the maintainers of FRR, and also Dr. Helen Chen and Dr. Feng Zi are going to present as well. Hopefully they'll be here. All right, so what are we going to talk about? We're going to talk about OSPF v3 over IPv4, and this is going to be by Dr. Helen Chen and Dr. Feng Zi. And I'm going to talk about BGP memory optimizations, FRR infrastructure changes, and if there's any time left at the end, we'll come back and talk about the releases.
So this presentation is about OSPF v3 over IPv4. And we'll start with a little bit about OSPF. So OSPF comes in two flavors, OSPF v2 and OSPF v3 today. And they were originally designed such that OSPF v2 only runs on IPv4 and OSPF v3 only runs on IPv6. And so that means that unlike other popular protocols like BGP or ISIS, you have to have two daemons running if you wanted to support IPv4 and IPv6. That was before, though. OSPF v3 has changed since the original specification that supported only IPv6. In RFC 5838, OSPF v3 added the support to carry IPv4 addresses, the PDUs, the LSAs, and the hellos, basically the OSPF messages still had to go over IPv6. So imagine it's IPv6 header carrying PDUs. But the PDUs can now advertise IPv4 prefixes. After that, RFC 7949 made a change such that now OSPF v3 could OSPF v3 PDU could be carried over IPv4 header. And that makes OSPF v3 essentially dual stack, that it can not only can it advertise IPv4 and IPv6, it can also operate both on IPv4 and IPv6, one or the other or both. So that's a little bit of the history. Do you have the other set of slides? The idea.
Do you want the other set of slides?
Yes.
Okay. There you go.
Okay. How do I see it? Oh. Okay.
I don't know.
Okay. Got it. So can you go to the next slide? And the next slide. So this was the original. So this is just a diagram of how it works. That now you can carry. OSPF could be run over IPv4, IPv6. Next slide, please. So in this slide, I wanted to emphasize that it's not tunneling that we're talking about. We're talking about directly having OSPF PDU carried over IPv4. And it looks like what you see on the screen. So the packet, of course, starts with IPv4 header. And then after the IPv4 header, so in the IPv4 header, you specify protocol 89. And that is just the OSPF protocol number. And it works for both. It's the same for both OSPF v2 and OSPF v3. The only difference now is that in the protocol header, instead of using version 2, in OSPF v2, you would have the IPv4 header with protocol 89, and then in the PDU, you would start with version 2. So that's the first 32 or first byte. But if you wanted to carry OSPF v3 packets, then you would specify version 3, and that's what's highlighted in this in the 3 in the OSPF v3 header. So again, this is just to emphasize that we're not talking about tunneling. This is really IPv4 directly carrying OSPF PDUs. Next slide. So the next two slides talk about what changes in the IPv4 header to carry OSPF v3 packets. The source address would have to be an IPv4 address. That's as expected. The next slide about the destination address. So OSPF has two types of packets, one unicast and one multicast. And so for the unicast, the destination address would have to be the unicast, the IPv4 address. For multicast, the OSPF packets would be sent to the original, the addresses or the multicast addresses that were defined for OSPF v2. So it's the all SPF routers and all routers. Okay. So that's the mechanics. And if you could go back to the other set of slides. Yes, the motivation. Next slide. The reason that we want to do this, so I guess there are two aspects. One is the existing networks. There are a lot of IPv4 networks that we have no ability to upgrade or with very difficulty to upgrade. It could just be the mechanics that you have to renumber a very large network, or it could be that the network, the links are very slow and we couldn't support IPv6. And for those networks, if you wanted to take advantage of the new features, which are mostly added only to OSPF v3, then the advantage of this approach using OSPF v3, but still running on IPv4 will give you that. So let me just restate that. If you run OSPF v3, you can get the more modern extensions. And if you run OSPF v3 on IPv4, you can have all those new additions, all those new features on your original network. So those are the reasons that we might want to use this approach. So the next slides will talk, Feng will go into the details of the implementation.
Thank you, Helen, for the introduction. So we implemented this feature on top of FRR 7.3. This version of FRR already supports OSPF v3 for multi-address family, which is the prerequisite for 7949. With the support of 5838, our implementation has been quite easier and also very straightforward. So we introduced at the data structure level, we introduced a new IPv4 socket to the OSPF v3 instance. So in addition to the IPv6 socket, right now we have both, one for v6 and one for v4. And then at the neighbor and interface level, we add interface address that we used for IPv4 as the transport. We also add two flags, one at the instance level, one at the interface level, to indicate which transport the user plans to use. So at the data structure level, the addition is quite minor. One more socket, one flag, and then one IPv4 address. As far as the code enhancement is concerned, I think the most of our enhancement is in the socket and then packet processing incoming and outgoing packet. So as we mentioned, we create IPv4 socket to handle OSPF v3 PDUs carried by IPv4. And we modified the existing logic to process incoming and outgoing OSPF packet. And then we also need to make minor modification to the socket options. And the second areas of enhancement is OSPF interface finite state machines. We need to make a small modification to the interface level finite state machine so the interface can be brought up even if there is no IPv6 address, because right now OSPF-v3 can use IPv4 as the transport. We also modify the neighbor finite state machine so OSPF-v3 can join a different multicast group using IPv4 options. And the next area we enhance is the BFD, because OSPF-v3 can work with BFD to detect neighborship changes and interface changes. So we have to use IPv4 address instead of IPv6 address. So I think the last but not least, we also implement the configuration part or the network management part to allow the user to control whether a certain we want to have IPv4 as the transport for a certain interface. So in summary, for the code changes enhancement, we have network management enhancement, socket enhancement, and BFD enhancement, and also OSPF interface finite state machine, neighborship finite state machine enhancement. So enhancements are considered quite minor. Fortunately, we found that in the existing OSPF-v3 enhancement, all the LSDBs and SPF calculations, they all support multi-address family. So that made our life really easier. Next slide, please. Yeah. We also want to highlight some design consideration we have when we implement the user configuration. Because we faced different options, whether to place the user control of IP transport mechanism at the interface level or at the instance level. At the end, we decide that we should have both, one at the instance level, one at the interface level. This is to achieve a balance between scalability and also granularity of control, right? At the interface level, the user gained more granular control, but at the instance level, one configuration can apply to all the interface, right? It's more scalable. So we have control at both. And then we set up a set of rules to make sure that there's no conflict, right? So if you have control at both levels, then the control at interface level will take precedence. Otherwise, if you only have the control at the instance level, then all the interface will inherit that from the OSPF instance. In our design, we also need to consider the changes of IP address. An IPv4 address can be added and removed from an interface, right? And then the control of transport mechanism can be turned on and off at a different level. So we have enhancement to handle these different cases. Yeah. Next slide, please. Yeah. So at the end, as a result, we implemented IFC 7949 on top of FRR 7.3. The enhancement is quite minor and complies with the existing OSPF design and implementation. And we feel like, as Helen mentioned, that this feature can help to facilitate migration from IPv4 to IPv6. And also, it helped to reduce the bandwidth requirement when using IPv6 or OSPF-v3 on top of IPv6. Next slide, please.
I think that concludes our presentation. There are some other, we performed a bit of packet analysis, but that's the details are in the paper.
Yeah. Yeah. Okay, thank you.
Thank you, Helen and Feng. We'll go with the BGP memory optimization first. So why do we care? So why do we care? So FRR runs on embedded systems, and a lot of times there's a very limited amount of memory that we can use. Additionally, there's actually no real good way to give memory back. So malloc trim exists, but the problem we've run into with using malloc trim is that it actually completely pauses your program from running. And when you're running a semi-real-time system where if you don't get your packet out, your peer goes down, having running malloc trim at random times will cause your peers to go down. And that's a destructive event and causes immense problems on your network. So, and if someone has a way that we can actually hand memory back to the operating system that allows us to not do it in a way that completely blocks the program for an arbitrary amount of time, I'd love to hear about it, but I don't know a way to do that. And finally, it's just good programmatic hygiene. You need to be careful about how much memory you're using and just watch it and make sure you're not using too much. All right, so recently there was a BGP RFC that increased the maximum packet size of data that could be sent. And when I say packet, I mean more a section of data from a BGP perspective, from like 4K to 65K. And when we did that, it ended up with a BGP peer and data structure that we had that was about 750K of data per peer. And when you're running BGP with several thousand peers, you're all of a sudden you're talking about your peer and data structure is, tens of hundreds of megabytes, which is not a great thing to do. And I went one day I was just looking at the code and I realized that we have a lot of data structures that aren't being used. A great example is this peer iBuff scratch. It was located in the BGP max packet size times 10 packet space for reading of data off the wire. But that is something, since BGP is single threaded for reading data off the wire, that can become a static data structure inside the function itself. And that just eliminates 655K of data. We had a withdrawal low in the struct BGP synchronize that was just never used, and that was like 8 bytes per BGP struct synchronize. The peer sync Affimax, Saffimax is a struct BGP synchronize, and it was just never used. It was allocated on startup, and at shutdown for that peer, it would delete it. And there was never any place in the code that was ever used. And I think that one, and these are all examples, like the rest of them are all examples of code that went into FRR at one point in time, was used for something, someone made an improvement and didn't remove the changed data structure. The peer OBuff work, that was ostensibly supposed to be used for output and buffer, but we never used it. Peer scratch, again, never used. And peer last reset cause is the reason why a BGP peer in session has gone up and down. I mean, down and then back up. And we save it as a last reset call so we can output it to the end operator about what's going wrong. And we were just allocating an array of 65K, but not your peer doesn't always go up and down for any reason, and it was just wasted memory. So when we went from FRR 8.5, the struct peer was 740K, and with the 9.0 release, we have 20K bytes of peer and data structure. And I guess the lesson I kind of learned from that is that it takes a lot more programming heuristics, no, that's not the right word. It takes a lot more work on the maintainer's parts to go through and actually have an understanding of what's being used and actually fixing it. All right, so the next thing I want to talk about is the struct BGP dest breakup. So FRR stores prefix information in a specialized data structure, binary tree, that the parent node contains a left and right pointer, a balanced left and right pointer for the individual prefixes. So like on the slide here, if I have a 111032 prefix and a 111132 prefix, they'll have a parent node that contains both of them with a longer prefix match, not a shorter prefix match. And FRR builds the entire tree all the way up to the parent, the top node, which is the quad 0 for V4 and V6. It's a full 0 nodes. And that's about 200 bytes for each BGP node and BGP. And the reason why we want to break this up is that a full BGP feed of like, say, 900 plus 1,000 routes has 1.4 million struct BGP dest nodes. And the nodes that don't actually have data associated, BGP data associated with it, we were allocating BGP data for. So what we ended up doing, we used the struct route node for all as holder nodes, and if we had BGP data, we have an info pointer off of it which points to struct BGP dest. So the end result is that the struct route node is now 120 bytes, the BGP dest is 96 bytes, and that saves about 30 megabytes per full BGP feed. All right, so another thing that, well, before I wanted to go, let's talk about BGP input-output queue memory optimizations, and before I get into that, I wanted to talk a little bit about how BGP does I/O. There's actually three BGP P threads. Sorry, there's three P threads in BGP. The main P thread, which is used for processing of data and figuring out what's to do, and generates data and hands it, and when it generates data to send out, it hands it to the I/O P thread to send out. The Keep Alive P thread does nothing more than generate regular BGP updates that are then handed to the I/O P thread for shoving out the door. And finally, the I/O P thread, which does nothing more than read incoming data and output going data. Now, one of the problems that can happen in a network is that you have an interface flap and BGP is going up and down, a BGP peering is going up and down. And what that ends up happening is that we ended up having hundreds of thousands, millions of stream data being stored for passing to our neighbors that we just haven't had a chance to send yet because the TCP stream is slower than the speed that we can generate data. And BGP has an OBUF FIFO for actual data output and an IBUF FIFO for input. And what we ended up doing was just stopped reading packets after we've received too many and allow TCP to back up and tell the other side to slow down. And for input and for output, we just stopped generating packets. And so here's a little bit of why it matters. So at the top, you see the NQ line, we have to the 194, 147, 139, 1 peer, we have 179,000 stream packets we're trying to process at one time that we have received and haven't processed yet. And in the V6 one, we have 314,000 packets. And you can very quickly get into situations where the input and output is completely swamping BGP with stream data, and all you're doing is just holding data in memory. And at the bottom, you can see that the limit we're just stopping instead of reading, continuously reading. And that actually saves quite a bit of memory. Next thing I wanted to talk about was the struct BGP path info extra. All right, so each prefix in BGP has a BGP path info, which is the peer data structure associated with the path data structure for that bit of data for that prefix from a particular peer. So in this case, we have three BGP path infos. That means we have 3 different peers sending us data about that particular prefix. And if we're not doing V4, you end up with a new data structure called BGP path info extra, which is extra data for non-standard AFIs. And I'm using that a little bit loosely because IPv6 isn't non-standard, but that's where we were putting the data in the BGP path info extra. And so, and for EVPN AFI, the EVPN AFI SAFI and the flow spec and labeled unicast, whenever I had that data associated with a prefix, I would create a BGP path info extra. But it's impossible if I am using EVPN to have flow spec data at the same time. So every single bit of time that we would allocate BGP path info extra, we would also be generating data structure size for those other AFI SAFIs that we weren't going to be using necessarily. So what do we end up doing? We just basically broke up the BGP path info extra to add in a few pointers, removing the specialized data structures and put them in their own. And that allowed us to go from a struct BGP path info extra from 432 bytes down to 176 bytes. And that actually made quite a bit of difference on people who are doing things like VPNs or EVPN. And this was especially important for the VPN case because you can have millions of prefixes. And that's a large amount of data that you end up, extra data you never use that you're allocating. All right, so FRR has this idea of ZAPI, which is the ability for daemons like BGP or OSPF to send route announcements to Zebra so it can install it into the kernel. And what we're currently doing is that Zebra currently tries to read as much data as it possibly can, and it saves that in a stream data, and when it can process it, it comes back around and processes it. Well, the problem with that is that BGP's flapping above me, and it's sending down a stream of data to me for route installations, where I'm just storing individual route installations as each individual streams, and BGP and Zebra can generate that data faster than Zebra can consume it, and you end up with a large number of streams that just end up as extra data. So what we need to do is have a little feedback mechanism where Zebra can signal to upper level protocols that I need you to slow down sending me data. And realistically, this is really just a BGP Zebra communication issue. Most other routing protocols don't have the possibility of millions of routes being installed at one time. And I don't think, we haven't seen this programmatically as a problem anywhere than just BGP and Zebra. All right, so I will talk a bit how Zebra handles the incoming data. So currently, we have a pthread per zserv per client connection. So BGP will have a pthread for read and data. OSPF would have a pthread for read and data. And all that Zebra does is that while there's incoming data, I grab the packet of data, I stuff it in a stream, and I place it on an input buffer, and then I do that as fast as many as I can, and then once I've got no more data to read, I signal to the main pthread to wake up. And the main pthread at this point in time wakes up, grabs 1,000 streams off of the FIFO, and then just processes each stream and does that in a loop forever if there's incoming data. And the real solution is just to stop processing new data on the zserv pthread for the incoming data, for the incoming client. And just leave the main pthread alone and just let it continue processing as fast as it can. And that will stop allocating streams, and it will force the, it will allow us to signal through I/O mechanisms to upper level protocols that they should slow down. All right. So how does sending data to Zebra work from BGP side? We have this idea of a buffer where when you call a buffer write, we will attempt to write the data to the file descriptor, and if we receive an ewood block, we immediately just save the data to the side on a buffer data structure, and we return a buffer pinin. And if it wouldn't block, we just write it to Zebra and continue on. And in the Z client signed message, when we get a buffer pinin, we just schedule a wake up via the event add write mechanism to write when we can write to the file descriptor. And so it allows us to save data. We'll save the data to the side instead of sending it down. And you can see down at the bottom here that we have 86, we have 86 megabytes of data that we haven't sent down to Zebra that BGP's holding on the side. Now, one of the problems with this is that if I have a link that's flapping, I can have a route that is going from three-way ECMP to four-way ECMP back to three-way ECMP, and instead of, and then what ends up happening is that BGP will write the three-way ECMP route installation to Zebra. That will be saved on the buffer, and then it'll write the four-way ECMP, and that'll be written on the buffer, and then the three-way, and we end up having 3 or 4 and 5 instances or multiple instances of route replaces where we're bumping up and down Nexthops. And that's actually vastly inefficient from multiple perspectives, in that Zebra will eventually read all those, and it'll do the route add and delete, route replace for each and every single one. And that's just a lot of extra unnecessary work. All right. So I want to talk a little bit about how BGP, and I kind of alluded to this in the previous slide, but I want to talk a little bit more about it. So BGP receives packs of data from peers, and we pass that to the master pthread for handling, and we decode it, we run bestpath, and then we install the selected route into Zebra, and that's how we currently do it. So what I want to change it to is I want to effectively store the David, your eyes went up. All right, so I effectively want to save to the side a list of items that I want to install into Zebra, and when the buffer is full, I'll go and write those. But and by doing it, we can prevent the multiple reads and writes, like I said in the previous slide. So what I want to do is create a new node that is a new FIFO that is stored off of the struct BGP master for routes that we want to announce to Zebra. When we decide that we want to write it, add a new route or delete a route, we'll add the node to the FIFO, and when the FIFO, and then we'll schedule a event to wake up and call and to start at the top of the FIFO and start doing route installations. If a node's the upshoot is that if I have the same node, I won't have it on that list multiple times. I can just leave it in that same spot. And when I finally get around to writing it, I'll write the last bit of data down to Zebra instead of the multiple up and downs. All right, so the next bit that I wanted to talk about is the some FRR infrastructure changes that I'd like to do and am currently working on. All right, so one of the things that BGP is doing is that it has a peer data structure per incoming and outgoing connection. And the finite, and so I guess I should take a step back and talk a bit about how BGP works. So on, if I'm a BGP speaker and David's a BGP speaker, upon startup, we both get our configuration, we read it in and go, oh, David's my neighbor. He goes, oh, Donald's my neighbor. And we both can open connections to each other at the same time. So when I say incoming from peer, that means I'm receiving a TCP connection from David to me. And when I say outgoing to peers, I'm opening a TCP connection to David from me. And what happens in BGP currently is that there's a state machine that goes, oh, one of these connections has come up enough, we're going to go with this connection. And what BGP currently does is it consolidates down to one peer and throws away the loser data structure after consolidating. And the problem with that is that we have two data structures, and part of the BGP peering is that we have a negotiation between each other about the state and what we'll be talking to each other about. And you end up with, if I'm throwing one of the data structures away, I need to transfer that data from one peer data structure to another peer data structure and keep one of them. And when someone adds new connection ability or a new feature to BGP, I have to remember to go in and to peer xfercon and peer xferconfig and make sure that I transfer that data over. And frankly, about twice a year, we're fixing a bug where someone has forgotten to do that. And frankly, it's just bad design. I want to fix it. So what I'm going to do, I'm going to create a data structure for the connection, and I'm going to call it struct connection, and I'm going to transfer the finite state machine to be connection oriented instead of peer oriented. And I'm going to create a connection for the incoming peer and a connection for the outgoing. All right, so some of this work's already been done. I have the two pull requests here, but effectively the first pull request created the struct connection and abstracted the allocation and deallocation of memory and started passing around the connection instead of peer. And the second one was an extension of that, which continued finding the places that we need to use connections instead of peers and switch them over to it. And we converted the events for BGP IO, BGP packet.c, and BGP FSMC to use a connection. And so what's left is I need to go through now and the places where we consolidate or decide to keep, instead of having two peers, we need to have one peer and two connections. And that's what's kind of left, is that all the setups in place. I just need to go through and finish moving everything around. And I think things will be much better. All right, the next thing I wanted to talk about is BGP bestpath reorganization. Currently, when BGP receives path info from peers, we shove it onto the top of the list, and it's ordered in reverse from most recent received to the first received. And the first received will be on the bottom. So on this slide here, we have 3 different paths that we've received, and you can see that the time for each one received is after each, it's in reverse order. And why is that a problem? The problem is that, well, I'm getting ahead of myself. All right, so why is it a problem? Is that we don't actually keep in any sort of order the path info from a peer. And why does it matter? So the current algorithm, what it's doing is that when I receive new NLRI information, I create a struct BGP path info, and I shove it onto the list. And when I finally run bestpath, I set my best to null, and then I loop over each struct BGP path info, and if the current one I'm looking at is better than best, best becomes current. And then I go back to the top and do each one. So I'm running bestpath for the entire list, even though I run every single time I run it, so I have to run bestpath 3 times for it, and I have to do it over every single node in the list. Additionally, if I have multipath enabled, I run bestpath again over every single item in the list. And since they're unordered, I can't stop when they're no longer better. So what do I want to do? I want to grab when I get a new path info, set it as unsorted, put it on the top of the list, and then grab the first unsorted item and find the first BGP path info without the unsorted flag, and that's going to be the best because that's I've already sorted off of it. And then I'm going to run BGP path info compare for the unsorted versus current, and if current's better, I'm going to take current off the list and put it in that spot and continue on, back up to the top of the while loop. And then if the unsorted is better, I'm going to place it on the list. And that will leave me with a sorted list of best paths. And when the unsorted gets to the correct spot in the list, we stop processing and stop looking at it. So why does this really matter? This matters like if I have 16-way or 32-way ECMP, it doesn't matter so much for if I have 1 or 2 BGP peer connections, because who cares what order things are in if I have a list of 1 or 2 and I'm running best path over. But if I have 16-way ECMP or 32-way ECMP, every single time something changes in the network, I have to do 32 times 2 comparisons, which is quite a lot. We don't really want to do that. So for the in-path comparison, when I'm sorting the best path, I want to keep track of why in-path is better or not, and I can just stop walking the list. I can just walk the list from best to where in-path no longer matters, and I can stop as well. So the main thing that I can prove this is correct pretty easily. What really becomes hard is that there are a lot of test systems out there that assume a specific order of the BGP best paths, and they will fail. And what I'll end up having to do is I'll have to go and convince all these different people that the change in ordering of the display hasn't really changed what my best path is. And that's going to be the hard part it's going to be a social engineering part from that perspective, convincing people they need to go fix their tests. And that's why I'm specifically calling this out, because we're changing the order of events, of how things look, tests will fail. Because tests were poorly written. All right. I want to talk about the Zebra data plane cleanups that are going on right now and how we continue to plan to do it. So when the data plane was originally added to FRR, we wanted the idea of have the ability of allowing operators to choose the correct data plane for whatever they're talking to. So if I'm using a Broadcom ASIC, I want to be able to use the Broadcom data plane. And if I'm using a Mellanox ASIC, I want to be able to use the Mellanox ASIC. So I shouldn't say operators, developers, people developing FRR to be used on their particular switch and platform. And mainly we wanted to do that is because data planes have different functionality. And we wanted to be able to abstract a generic way of thinking about the problem. I don't want Zebra, the main part of Zebra, to behave differently because the ASIC is behaving differently. I want it to be intelligent and just be able to say, hey, install this route. You figure out the details. I don't care about that part. So we also want a FRR to have a p-thread that is in charge of the talking to the data plane. And one of the key factors here is that we want it to have a context that we can pass down from the upper level and back up from the data plane itself to Zebra itself about the change that is being talked about. And the other part of that is that we want it to ability to prevent the data plane from accessing the Zebra master p-thread data structures. They should be separated, and we shouldn't be poking into each other's memory. And the final thing we want it to do is that FRR should be able to receive asynchronous data plane updates about anything and process it accordingly. All right, so what did we ended up with? We ended up with a mess. We have 4 netlink sockets in Zebra for handling different types of commands. All right, so there's the netlink and netlink command sockets. The first one, netlink, is to receive netlink notifications from the kernel based upon groups. This runs in Zebra's master p-thread. And netlink command is the Zebra master p-thread sending a netlink command to the kernel. And then we have the netlink dplane out, which sends batching data to the kernel when it receives a context. And we have netlink dplane in, which receives information about dplane groups. And what ends up happening was that the netlink command socket would receive data about particular groups, and it would be scheduled for reading at some point in time in the future. Then the data plane in socket would receive information from other netlink groups, and it would pack that up into a context and pass it up to Zebra. Well, the way Zebra p-threading works, the way Zebra events, the way FRR events work is that we handle events and then reads and writes. And so if Zebra is especially busy, we can have events from the dplane that have dependencies on data that the netlink command hasn't been read yet, and we'll go, oh, you're sending me data about something I don't know, let's drop it on the floor. And do I have it? Yeah, so the problem is that, like, under heavy load processing, the interface creation events would come in on the netlink, and the interface address events would come on the data plane, and the address events would be handled first in Zebra, and we would drop them, and we would not end up not knowing about address information on Zebra. So what we did is we just moved all the interface creation and deletion netlink events to the data plane in the group. We moved the our team in group link from groups to dplane groups, and each individual netlink message became a context message that was passed up to Zebra, and then we preserved ordering because address events would always come after that. And so what we end up having to do is that every single group listed here, in the first one in groups, needs to be moved under to dplane groups, and we just got to go through and do them one at a time. So that's the change that we need to end up doing. All right, are there any questions? All right, so I want to do a really quick walkthrough of the changes since the last workshop. And this is by no means comprehensive. If you wanted to see for yourself, you can go look at the release notes. But in 8.4, we have the big one, I think, is the BGP site of origin support, which is really useful. And the other one is the PIM v6 support with MLD. We now support PIM v6, which is pretty awesome. In 8.5, there's PIM v6 BSM support. I wanted to call out the deprecation of shell commands. There are some commands that are security holes that we supported for a very long time. And I say security holes because you can, in V2I shell, you can invoke a command that drops you into a shell, and you can have elevated privileges. And then frankly, that's just not great. So we've deprecated those finally, and they're going through a deprecation cycle. So I wanted to call that out. All right. And 9.0 was this last summer's release. The big one, the big thing I really want to talk about here was the upgrade to Libyang 2.180. So if you're using FRR, you need to be careful about the version of Libyang that you're using. The Libyang group, the Libyang developers are making changes that are sometimes backwards incompatible with current versions of FRR. So always test Libyang 2 and make sure you're not using something that doesn't work. And I mentioned 2.180 specifically because that's something that we've tested with ourselves and what we use internally. Later versions, there are later versions of Libyang 2 that just don't work. So just be aware of that. The other big thing that came out with FR 9.0 was the addition of management E. So the goal of management E was to consolidate the CLI and configuration and operational data into a single management daemon. It gives you better control over configuration validation. It provides commit and rollback, commit validation, commit and rollback. So you can roll back to previous versions. And for 9.0, the really big change is that the one that was converted was static D. In future releases, I know OSPF's coming in, Zebra's coming in soon, as well as RIP. Those are the ones that are being worked on currently to come in next. So I wanted to do a quick example of what what commit validation is. So I added a route 123.432, and I did a do show IP route static, and it's not actually installed yet. And if I enter the configuration with file lock, which says I'm about to make changes to the CLI, but commit them all at one time when I'm done. And then you can do like do show management data store contents candidate, which shows that we have a static route that is being ready to be installed. And then on the right, we have management commit apply, which applies it. And then I can see that the static route was installed. And then I can also at this point in time go, I don't want that, and roll it back. I didn't show an example of it, but I think that's kind of neat that I have the ability to keep track of what I was and where I'm going from a CLI perspective. Oh, and the other thing I wanted to talk about was there was a draft RFC that allows you to pass your BGP software version to your peers. And I thought that was kind of neat. I can pass to my neighbors what version of FRR I'm running. And other non-FRR routers can receive that and send us theirs. And I think it's kind of really useful from an operational perspective. If I have a large network, I can quickly run a show BGP IP for Unisum and get the list of what my other versions are. And I think that's kind of useful. All right, so 9.1 is going to be released in probably a month, a couple weeks to a month. I'm not entirely sure off the top of my head. But it's going to have a bunch of new features that you can read about here. The last thing I want to talk about is that we've had a couple snafus recently where CVEs came in that weren't properly communicated to us, and we dropped the ball on it. And I wanted to reiterate with people that if you wanted to talk to us, here's how you can talk to us, especially from a security perspective. If you need something or you think you discovered something, email us at security.list@list.frr.org. All right, any questions? All right, thank you, everyone.